So this will be the fourth lecture over chapter 14. So in this lecture, we'll look at how to make epoxides and the reactions that epoxides undergo. Okay, so we've already looked at how to make epoxides in a previous chapter, so chapter 8 from Organic 1. You can take an alkene with this reagent MCPBA. So that's the structure of MCPBA. It's just an acronym for metachloroperoxybenzoic acid. So if you take an alkene with MCPBA, so we won't go through the whole mechanism again, but basically what happens is that oxygen gets transferred here to make an epoxide. So just take the double bond and make an epoxide out of it. And then if you bump the hydrogen down into its place, then you would make that side product, which is metachlorobenzoic acid. But that would be our main interest. So that's one way to make an epoxide is MCPBA. So you should know both the acronym and both the structure and both the name. Maybe you would see any of those wrote on the arrow. Okay, so in this chapter we'll look at one new way to make epoxides. So a two-step sequence of reactions. So the first step is an old reaction. If you take an alkene with Br2 and water, so that's a reaction from chapter 8. So if you remember what happens there is that adds bromine and OH across the double bond, anti to each other. So now once you have this compound, if you take that and react it with sodium hydroxide, then what this is going to do, so you can take a lone pair on hydroxide and deprotonate the oxygen of the alcohol. Right, so now you have the conjugate base, the alkoxide version of the alcohol, and that's a good nucleophile. And you have a leaving group in the same molecule, so this can do an SN2 reaction. So as soon as you make this, it doesn't stay there. This oxygen reacts here, and you kick off the bromine. And now you have an epoxide, right? So you react an alkene with Br2 water, that adds bromine and OH across a double bond, anti to each other. And then once you have that, you react it with a base like hydroxide, which takes the hydrogen off to make the conjugate base of the oxygen, which is a good nucleophile. And it doesn't stay like that. As soon as you make that, then it doesn't, that would be an intramolecular SN2, right? Means within the same molecule. So oxygen attacks carbon, kicks off the bromine, and that forms the three-membered ring with oxygen and then the epoxide in the process. Okay, so to summarize, two ways to make epoxides, so alkene and MCPBA, or you can do the two-step sequence, Br2 and water, or it could be Cl2 and water. You could add the chlorine and OH anti to each other, and then once you have that, then you react it with NaOH or any strong base, and then that would make the epoxide. Okay, and then in terms of reactions of epoxides, so we'll look at two different classes of reactions, one that are called Basecatalyzed, and those are SN2-like, and Acidcatalyzed, and those are SN1-like in their nature. Okay, so we'll look at the Basecatalyzed first. So all of these are Basecatalyzed. Okay, so LiAlH4. So if you remember, when you see that, you can think of that like a source of H-. So what's going to happen if it's, so we have two carbons that are partial positive, right? Both of those carbons of the epoxide are partial positive. So that's where the nucleophile is going to be attracted to. But if it's SN2-like, which one would it prefer to react at? So this carbon on the right only has one carbon attached to it, so it's primary. And this one on the left has two carbons attached to it, so it's secondary. And SN2, since it's SN2-like, then primary is going to react faster than secondary, which is going to react much faster than tertiary. So that means the nucleophile is going to react here, and then we're going to open the epoxide bond that way. So in all of these reactions, the epoxide gets opened up. So nucleophile, if it's base-like, nucleophile attacks the least substituted carbon and opens the epoxide up. So the oxygen takes the electrons in the carbon-oxygen bond. So now that carbon has an extra hydrogen, so it's a CH3. And then you do the second step, you do the H+ step. And that's just going to add the hydrogen to the oxygen. So take a lone pair on oxygen, make a bond to hydrogen. And that would be your product, right? So all of these reactions are similar. So the nucleophile, so if you Grignard reagent, if you remember, that carbon is partial negative. So that carbon is going to attack here and open the epoxide to make the O-, which will pick up a hydrogen in the next step. So you would make so benzene would be attached to CH2, or whatever's attached to magnesium would be attached to the CH2, and then you open up the epoxide such that the OH ends up on the CH. Or if it's an organolithium reagent, right, that carbon's partial negative, so that carbon would attack this carbon and open the epoxide. So all of these nucleophiles attack the CH2 because it's the least substituted carbon. So then that would become an O-, which would pick up a proton from the H3O+. So that would be your product, right? Or if it's Cn-, so Cn would attack this carbon, make an O-, which would pick up a hydrogen in the second step. Right, and that would be your product. Or if it's RS-, right, doesn't matter what the R group is, could be CH3 like it is here, it could be a 100 carbon chain. So sulfur attacks this carbon and opens the epoxide. Right, and again you make O-, which picks up a hydrogen in the second step. So if you notice in all of these, the H+ is in the second step. Okay, if it's hydroxide, so OH- is the nucleophile, would attack this carbon and open the epoxide. So the O- would pick up a hydrogen from water, so you would remake hydroxide in that reaction. Or if it's NH3, then nitrogen, sorry, it's getting a little cluttered now, but nitrogen attacks CH2, opens up the epoxide. And then nitrogen loses a hydrogen. And then the O- picks up a hydrogen, picks up that hydrogen from the nitrogen. Right, so again, NH3 would attack the CH2, open the epoxide up to make the O-, and then you would lose a hydrogen from the nitrogen, and that oxygen would pick up the hydrogen. So you end up with an NH2 added there instead. And sorry, this has got a little cluttered. Let's see if I can move some things down so I can sketch that last reaction. Okay, so same concept for the last reaction. So our O minus is a good nucleophile. So take a lone pair on oxygen, make a bond to carbon, open the epoxide up. And then the O minus picks up a proton from the solvent. So in the previous example, it picked it up from water. In this case, it picks it up from the alcohol. So take a lone pair on oxygen, pick up a hydrogen, and you remake OCH3 minus in the process. And that would be your major product. Okay, so if we took some other examples that introduces another level of complexity, well, what if you have stereochemistry in the molecule? So if you remember how SN2 reactions work, you get inversion of stereochemistry. So this carbon that's partial negative would have to attack from opposite of the leaving group. The leaving group in this case is the epoxide, so to open that oxygen, carbon-oxygen bond up. So the oxygen stays on top, right? But the hydrogen here would have to flip to the front as the nucleophile comes in from the back. And then in the next step, you pick the H plus up on the O minus. Right, so that would be your product. And if it's lithium aluminum hydride, then again, this is just H minus as your nucleophile. So it would just be an H minus attacking here. And you would end up with at the end, you would get that, right? Because you're going to add, so the carbon on the bottom is going to end up with two hydrogens on it in that case. So there's no stereochemistry there anymore. And if you used hydroxide as the nucleophile, then a hydroxide would attack this carbon. Right, so the carbon on top, nothing's happening to the stereochemistry there because there's no reaction there. In this case, all of the reactions at the bottom carbon, so that's where the stereochemistry has been flipped at. So the hydrogen would have to flip to the front, and the OH would have to be on the bottom. And then that O minus would pick up a proton from the water. So take a lone pair, pick up a hydrogen, OH electrons become a lone pair. And you would end up with that. You would end up with the trans or anti one. You would end up with a OH-OH anti to each other. So if we contrast that, so we've seen reactions like this where you have cis or syn 1,2 diols. Right, so you've seen a reaction in the past, chapter 8, how to add OH and OH across a double bond syn to each other. If you remember the reagents that do that. So you could do that with osmium tetroxide and H2S, or if you remember the other reagent that will do that, you could use cold potassium permanganate. Okay, so if you wanted to syn 1,2 diol, then you would oxidize an alkene with one of those two reagents. If you wanted to trans 1,2 diol, then one way to get there would be go through an epoxide that you react with hydroxide. Okay, so for the acid-catalyzed reactions of epoxides, so they're SN1-like. So let's see. So if we just contrast the two. So this is the least substituted carbon, and this is the most substituted carbon. For the base catalyzed ones, the nucleophile goes here, SN2 like. If it's SN1 like, that's what we're fixing to see, then the nucleophile ends up there and the OH ends up here. So basically we just flop where the nucleophile and OH ends up at, whether it's acid or base catalyzed. So if we look at some examples, so this would be some examples of the acid catalyzed reactions. And so let's go through a mechanism first of all, how these reactions occur. Let's get this out of my way. So we took this and reacted it with H plus Cl minus. So it's a totally different mechanism if it's acid catalyzed. And how do you know if it's acid catalyzed? There's going to be H plus in the first step in this the reaction. If you notice in all of these reactions where it's base catalyzed, H plus is in the second step. So here, if H plus is in the first step, then the first thing that happens is you protonate the epoxide. And then what happens is this epoxide starts to open up. So it could open up by stretching either of these bonds. So, and that will delocalize some of the positive charge to the carbon. So which bond would rather, which carbon would rather contain some of the positive charge density? Right, it would rather stretch the CO bond on the left to delocalize positive charge density. So now oxygen is not fully charged, it's partial plus and the carbon's partial plus, so some of that positive charge density is shared between oxygen and carbon because that bond has been elongated. So why would this carbon rather have the partial positive than this one? Because this is a secondary carbon, so this is carbocation-like, and that's primary, and the positive charge density would rather be on the secondary carbon rather than the primary carbon. And so now then the Cl minus adds. And so since this carbon is carrying positive charge density, the chlorine is going to attach to that carbon, and then you can finish opening up the epoxide bond. And that will be your major organic product, where the nucleophile Cl ended up on the more substituted carbon and the OH ended up on the less substituted carbon, which is exactly opposite of the base catalyzed reactions. And again, it's all because of this. Once you protonate the epoxide and it starts to open up, it would rather open up to put positive on the more substituted carbon, so that carbon becomes partially positive, and then that's where the nucleophile will be attracted to. Okay, so if we did that for this epoxide, so this carbon is tertiary, right? And this carbon is secondary. So it's better to put positive charge density on the positive tertiary carbon than the secondary one. So that basically means the nucleophile is going to end up on this carbon if it's acid catalyzed. And here it's acid catalyzed, here H+, here H+ is all in the first step. So this is going to give you, and so since you don't make a true carbocation, the nucleophile, it's SN2-like in the sense that it has to come in from the backside, but it ends up on the more substituted carbon. So here the bromine would have to come in from the backside of the oxygen, So bromine would have to end up back, and that will flip the methyl group to the front. And then the epoxide would open up, right, leaving the oxygen on top of the molecule. So that would be your major product, where the nucleophile is on the more substituted carbon. Or if it's water, then it would be an H2O molecule that would be attacking here. So that would flip the CH3 to the front, and water would end up there. Water would lose a proton in the course of the mechanism, and you would end up with that. Or if it's an alcohol, so our O group will end up attacking here, and then you'll lose a hydrogen from the alcohol in the course of the mechanism. So we'll just sketch this mechanism in its entirety. Well, if we were doing the mechanism, let's just do the mechanism here. Let's get rid of that. So if we were sketching the mechanism here, so first thing you would do is protonate the epoxide. And then let's open that epoxide up partially. So I'll use just a dotted line to represent that rather than a wedge. So now this carbon has positive charge density, and then that's where your nucleophile will attack at. So we'll take a lone pair on oxygen. It still has to come in opposite of the leaving group, and that inverts the stereochemistry in the process. Let's see. And then you lose a hydrogen from the alcohol. So the OH electrons become a lone pair on oxygen. And that would be your major product. And so again, if we contrast this to base-catalyzed, right, then the nucleophile would have to come in to that carbon. And that would be your major product. So again, if we contrast this to this, you get the opposite stereochemistry, right? Because the nucleophile attacks the opposite carbon. Okay, and so lastly, let's just do a synthesis problem. A couple of synthesis problems that utilizes some of the material from this chapter. So if we want to synthesize this alcohol, and start with cyclohexane and ethane, and use anything else that you want to use, but somewhere in the synthesis you have to use those two molecules to make this alcohol. Okay, so the first thing to recognize is that these two carbons come from ethane and this comes from cyclohexane, so you need to unzip the molecule there. And so you need to make a carbon-carbon bond. So if you remember what reactions make carbon-carbon bonds, so if we wanted to unzip this molecule, well, you could see that maybe this could come from an epoxide. And the hydrogen and oxygen came from the second step, H+, and then you could have had that as a Grignard reagent, right? So if you took this methyl cyclohexyl magnesium chloride with the epoxide, you would make that alcohol, which is what you want. And so now how do you make the Grignard reagent? Well, you make the Grignard reagent from the alkyl halide. So this was chapter 14. This is chapter 10 from Organic 1. And then how do you make the alkyl halide? Oops, arrow's going the wrong way. So you could have made the alkyl halide from cyclohexane, which is one of your starting materials, by doing a free radical chlorination. And that's chapter 4. And then how do you make the epoxide? You would make the epoxide from the alkene, MCPBA, so that's chapter 8. And then how could you, and you keep in mind you had to start with ethane, so how could you make alkenes? You can make them from alkyl halides. So if you had ethyl bromoethane, then you react that with strong base in heat to do an E2 elimination. That's chapter 6. And then you could have made this alkyl halide from Br2 and lighter heat, free radical bromination, and again that would be chapter 4. So in order to do the synthesis, so it's a 1, 2, 3, 4, 5, 6 step synthesis, which would be more than I would ask on a test, but that just illustrates to you how you can string together 6 different reactions through a convergent synthesis. So you get 2 pathways going to make the epoxide and make the greener reagent, and then you converge them into 1 pathway to make the final product. But it requires material from 1, 2, 3, 4, 5 different chapters. And so again, that's what makes organic chemistry difficult for a lot of people. It's not that any one thing is difficult, it's that there's a lot of material that you have to remember in order to do problems like this. Okay, so let's take one more. If you want to just synthesize this molecule, starting from this and anything else that you want to use. But you have to use cyclohexane somewhere in this, cyclohexene somewhere in the synthesis. Well, so maybe it's obvious that you need to make that bond at some point because you have a 6-membered ring here and you have a 6-membered ring here. So this probably came from that, and you added this separately. So how could we have done that? We could have done that if we had, so we could have made that ketone from this alcohol. Right, if we had that and we did one of these oxidations that you know of, PCC, PDC, KMNO4, chromic acid, dichromate, Sworn oxidation, right, one of those oxidizing agents would convert the alcohol to the ketone. And then how could you have made this alcohol? So we could have unzipped this here. So if we had this epoxide and reacted it with that Grignard reagent, right, then this would attack here and open the epoxide up to make O-, which would pick up a second hydrogen in the second step. So that would make that alcohol. And then how could we have made this epoxide? Well, we could have made it from that alkene with MCPBA, or we could have done Br2H2O, NaOH, right? How could we have made this alkene? We could have made this alkene from bromine, chlorine, doesn't matter. Right, through that E2 elimination. And well, we didn't have to go back that far because I told you got to start with cyclohexene. So we didn't need to do this, right? That was our starting material. So if we had that starting material and we made this epoxide, did this Grignard reaction to make this alcohol, and then oxidized it, then you would have the product, right? Okay, that's it for chapter 14.